Okay, good evening. This is Professor David J. De Los Reyes. Okay, my topic for tonight will be alternating current circuit, and this is an example of loop equations, meaning the determination of a current in a circuit, okay, by using the loop equations method. Okay, let's proceed. Okay, this is a continuation of my long video format discussion on alternating current circuit. So the topic for tonight will be alternating current circuit lesson number 34. And the title of the topic is example problem using loop equations. Or the topic for tonight is an interesting problem because it is one of the advanced methods on how to compute current circulating or current in a circuit under alternating current circuit. Without this, I think design engineers will be having a difficulty designing electrical systems because without knowing the current in a given branch of a circuit, okay, it's very dangerous if you don't know the exact value of the current. So we must have to know the exact value of the current by using our knowledge of loop equations. So electrical engineers are actually very uh, workaholic because without using the so-called complex fraction operation, okay, we could not compute for the current. Okay, let's proceed. We are given an alternating current circuit. Uh, we are given two voltage sources A2 and A1, and connected across the load is actually C sub L, meaning a load impedance. This C sub L could be the single equivalent impedance of a house, maybe a business entity, a big corporation. Okay, that's C sub L. So this C sub L is actually a complicated thing, right? But for tonight, we will just what you call this, summarize the value of C sub L by placing the value of C sub L to be equal to 12 plus J ohms. Okay? We are done with the computation of C sub L by using the series parallel combination. For tonight, the emphasis is actually on the concept on how to compute a current with any given circuit by using loop equations. Okay, these are the values. Z1, Z2, and CL, these are the values. C1 is the internal impedance of E1, Z2 is the internal impedance of generator number 2, C sub L is the single equivalent load, the one I am referring to a while ago, and voltage source number 1 is 250 angle 0, voltage source number 2 is 240 angle 15 degrees. The problem is only asking for the current passing here. What will be I sub L equal to by using loop equations? Actually, we could solve this problem by using the past methods of solution, that is the Thevenin's, Norton's, superposition, and nodals. But for tonight, okay, we will be using loop equations because the next time around, we might be solving this one again, the same problem again, and we'll try to check the validity of the answer, okay, by using one of the four methods that has been finished. Okay, so but for tonight, let's bring out the loop equation solution. Okay, the the solution will be something like this. Okay, we take the summation of the voltages considering I1. So I place it here, I1 loop, clockwise direction is a negative current. Okay, E1 considering I1 loop is a voltage source, it's minus or plus, so this is plus. The current circulating on I1 loop is I1, right? Like what I said, the current that goes with the tray should be negative. So this is minus I1, right? And the impedances that this I1 passes is actually Z1 and Z2. So this is multiplied by C1 plus C2. The product of voltage, or the product of current times impedance is actually voltage. Okay. We are now through with E1. We are now through with I1, considering C1 and C2. Okay. Let's try to get the effect of E2. The effect of E2, the polarity is different from this because the positive voltage source should be from minus to plus. But considering I1, if the rotation of I1 is like this, okay, the polarity will be from plus to minus initially, okay? So this will now be a negative E2, right? How about the effect of I2 considering I1 loop? Okay, there is. It is against, because clockwise direction for I1 loop is negative, but the effect of I2 with respect to I1 loop is against. So this is plus I2. It is plus. The voltage across this due to I2 will be the product I2 times C2, but the sign should be plus. Okay. If we try to simplify this one, I will go ahead with I1 first. So this should be I1 times the sum of C1 plus C2 minus I2 C2, and this should be equal to E1 minus E2. We just rearrange the summation of the voltages, right? This one here, we put it on the right. This one here, we put it on the right. Then we interchange location. So this will now be plus when it goes to the right. When this goes to the right, it will now be minus, right? And what remains on the left will be the difference E1 minus E2. We put it on the right. We rearrange. So it looks handsome, right? So this will now be E1 minus E2. We call this equation number 1. Considering the I2 loop, next one. Okay, that's why the topic is loop equation. We take the summation of the voltages, okay, considering this loop here. We start with E2 minus the plus, right? The trace is clockwise, right? Like what I said, the current that goes with the trace should be negative, right? So it is minus I2 minus this minus I2. The impedance in which this I2 passes is actually C2 and CL. So this is multiplied by C2 plus CL. Okay. There is an effect of I1 on I2 loop, okay? Because it passes through Z2, right? And it contradicts the negative direction, so this should now be plus. So the voltage drop on Z2 due to I1, considering I2 loop, will be the product I1 times C2. This is I1 times C2, but it should be plus, right? And this should be equal to 0. Okay, then again, rearranging this one, we put this one on the right, so this will now be negative. We put this one on the right, so this will now be positive. We will maintain the location of E2, so it will still be positive. It's on the left, but we rearranged already, so this will now become a value on the right. This goes on the right, but I will interchange location, right? So this will now be equal to E2. Meaning to say, the product negative I1 C2 plus I2 times quantity C2 plus CL should be equal to E2. And that will be equation number 2. Okay. The current we are looking for is actually IL. And this IL here is actually I2. Right? So if we could compute for I2, we could compute for IL. Since we are given two linear equations, linear complex equations, okay, equation number 1 and equation number 2. If we could compute I2 from these two equations here by solving it simultaneously, okay, we could compute for I sub L. Okay, let's try to rearrange. So because the proper solution of this one, if you are studying electrical engineering, the best solution of this one is actually, if there are two unknowns, you can use Cramer's rule or determinants. Of there are three unknowns, the best solution is still determinants. For unknowns, it's still determinants. You cannot use the elimination by substitution because it's a complicated thing. The Cramer's rule, you just follow the equation, take it easy, and you could come out for the proper solution accurately. Right? So if I will try to represent equation number 1 and equation number 2, I can rewrite it like this. A1 I1 plus B1 I2 equal to C1. That will be equation number 1. A2 I1 B2 I2 equal to C2. That will be equation number 2. This one is actually similar to the derived equation number 1 and number 2, in which we will just represent the value of A1 to be the coefficient of I1. So the coefficient of I1 is actually A1, right? And A1 is actually the sum of C1 plus C2. Where's A1? This one. Right? The coefficient of I1 on the first equation is actually the sum C1 plus C2. So we will just represent that one as simply A1. Okay? And the coefficient of I2, considering equation number 1, is B1. And B1 is only C2, right? That's C2. So this is actually B1. This C2. Right? And C sub 1, considering equation number 1, is the difference E1 minus E2. So actually, we put the calculation of that one to be this one here. So that's actually equation number 1. So by rewriting with this, we know the equivalent of A1 to be C1 plus C2, and B1 is actually C2, and C1 is the difference, E1 minus E2. Right? How about equation number 2? The coefficient of I1 considering equation number 2 is actually C2. It's also C2, this one. So this is actually equal to also A2. Right? And B2 is the coefficient of I sub 2 considering equation number 2. And B2 is actually the sum of C2 plus CL. That's why we computed C2 plus CL differently also. Right? So we now know B2. And what is the value of C2? The value of C2 is the right-hand side of equation number 2. That is actually E2. We now know E2. So this is actually C2. Right? So by using Cramer's rule, we are interested for, we should not have to compute for I1. We are just only interested in the value of I2, because if we have computed I2, we conclude that I2 is equal to IL. So we go directly with the value of I2 by using Cramer's rule. Okay? I will discuss Cramer's rule. It's like this. Current I1 is the determinant of I1 over the determinant D. Okay? And current I sub 2 is the determinant of I sub 2 over determinant D. We are interested in this one. Okay, it's like this in Cramer's rule. If we try to compute for I sub 2, okay, cover I sub 2, the column for I sub 2, right? Replace it with C1, C2. So this will be replaced by C1, C2. So the matrix for I sub 2 will be A1, A2 plus the replaced value C1, C2. So it is actually A1, A2, right? A1, A2. We are computing for I sub 2. So we get this column here, we place it here. So it will now be, the matrix will be C1, C2. Okay? And the determinant D, it's easy. It's just the coefficients of the left hand side. That is A1, A2, B1, B2. So the determinant will be A1, A2, B1, B2. Actually, if we try to simplify this one, it should be the product of the downward motion. A1, C2 minus the product of the upward motion, A2, C1. Right? Again, if we try to simplify this, it should be A1, B2. right? Minus the product of the upward thing, A2B1, A2B1. So if we could compute for A1C2, you subtract that by minus A2C1, you compute again A1B2, okay? Minus A2B1, we could now compute for I sub 2. Right? So it's just a matter of being systematic. Okay, let's try to compute for A1. A1 is C1 plus 2. C1 is given. C2 is given. Changing to rectangular. Converting to polar. This is the polar equivalent. This is the polar equivalent of the value C1, C2, which is actually A1. The one we needed here. Right? And how about B2? B2 is actually the sum of C2 plus CL. We are given C2. We are given CL. Converting to rectangular, this is the rectangular. Converting again to polar, the polar equivalent of the sum C2 plus CL is 15.22 angle 33.5 degrees. We are just being systematic and take it easy, okay? You cannot accelerate in the solution here. Just take your time and be accurate, okay? How about the value C1? We need C1. It's the difference of A1 and A2, right? A1 is 250 angle 0. A2 is 240 angle 15. Subtracting this one, converting to rectangular. This is the rectangular. Again, converting to polar, 64.716 minus 73.68. Okay? So to compute for let's try to take first the product of A1 and C2. We know A1, right? It is 1.3836.41. We know C2. Where's the value of C2? C2 is actually E2. That is 240 angle 15 degrees. Multiplying this one, okay? Then converting to rectangular, because later on we will subtract one here, right? This is the rectangular equivalent. How about the value A2C1? A2C1, A2 is, where's A2? A2 is C sub 2, 0.8 angle 30. Okay, am I still on the camera? And the value of C1, do we know C1? Yes, we have computed C1 already and we express it in terms of polar. That is 64.716, angle negative 73.68 degrees. Performing this, converting to rectangular, because in here we will subtract, right? Okay, this is the rectangular equivalent. And for the difference A1B2, A2B1, I didn't show you here anymore, but we could compute for A1B2. I don't show you anymore, we lack space. Minus the value A2B1. This difference is actually the denominator, right? Right? If you compute for this one, I have computed this one, but I cannot place it here, we lack space. The difference of A1B2 minus A2B1 will be 20.495 angle 70.22 degrees. So we now know the value of the numerator. We now know the value of the denominator. Okay, in terms of polar, this is the polar equivalent of the one. The difference of the numerator, that is A1C2 minus A2C1. So if we try to divide this, the operation is division, right? We now know the difference of A1C2 minus A2C1, but it's this. Right? And A1B2 minus A2B1, I have the computation, but I didn't place it here. Okay, we lack space. The polar equivalent is 20.495. So if we divide this one, polar over polar, okay, very nice, amen. Okay, what will come out for I sub 2, and which, that's actually I sub L. And this should be 6.225 angle negative 27.73 degree amperes. So that's the one, that's the current drawn by I sub L due to these two voltage sources. Okay, the current is 16.225. Okay, that's it, guys. Just take note of the answer, because the next time around we will check the validity of this, if this is really correct, by using one of the four methods. It could either be the Thevenin's theorem, Norton's theorem, what's the other one, superposition theorem, or the nodal theorem. We will just present one validity to check this one. Or we might use Thevenin's theorem. And supposedly what will come out will be still 16.225. Even angle, negative 27.73 degrees. Okay, that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.De If you want to share it, please click share. Okay, good evening from Los Angeles, Professor David J. De